Okay, so in this video set we're going to go through buffers, we're going to go through titrations, and a little bit on pH calculations and pH curves. You're going to need something to take notes with, something to take notes on. There won't be any math in this particular portion, so any of the math that we're going to do I'm going to attach in a separate video later. But once you have all those things ready, we can start. Now, if you haven't taken notes from a video before, the way I recommend doing this is listen to me give the lecture on the entire slide, then pause the video, then write down whatever it is you want to write down. This is how we're going to wind up being most efficient with your time. Alright, so we're going to start off talking about buffers. Now, where we left off, we talked about weak acids and weak bases and how to calculate pH based on Ka and Kb, and the relationship between Ka, Kb, Kw, pH, pOH, and pKw, which at 25 degrees is 14. Right, so here we're going to pick up a buffer. For those of you who remember this from biology, a buffer is basically just a solution which resists change in pH. So if I have a solution and I add acid to it, its pH isn't going to change that much. If I add base to it, its pH still isn't going to change that much. It kind of remains constant where it is. The way that we go about making these is we make these by combining a weak acid or weak base and its conjugate, right? So I have a few examples here. So we have the weak acid phosphoric acid. Its conjugate base is the dihydrogen phosphate ion. Or if we want to, we can make one with dihydrogen phosphate as our acid and hydrogen phosphate as our base. Or we can say hydrogen phosphate will be our acid and the phosphate ion will be our base. Now, when you're making a buffer, if you're using an ion, what you want to make sure of is that the ion is soluble. So use any soluble salt, basically meaning use any group 1 salt of it. Typically, you're going to use sodium salts or potassium salts because those are the most soluble. Right, so if I wanted to make a buffer with phosphoric acid, I would use phosphoric acid and sodium dihydrogen phosphate. If I wanted to make it with dihydrogen phosphate as my acid, I would use NaH2PO4 and Na2HPO4 as my two salts. Right, so I would use the same soluble ion in both cases. So this is the traditional way to make a buffer. The other way to make a buffer, and this is something that you're going to see a lot of, are what we call sneaky buffers. Right, because we can kind of backdoor this if we don't have one of the salts available. The way that we do that is we react it with a strong acid or a strong base. Right, so if I take a strong acid, say for example hydrochloric, and I react it with excess weak base, any weak base I want, I'm going to form a buffer. Or if I take sodium hydroxide and react it with an excess of any weak acid, that will also give me a buffer. So here's an example of how I can make this. Let's take hydrochloric acid and ammonia. If I mix together 1 mole of hydrochloric acid and 1.5 moles of ammonia, right, so if I have 1 mole and 1.5 moles, according to this equation, if we do our ice table, so here's I, C, E, stoichiometry says we're going to react all of the HCl and be left with none of it. We're going to react out 1 mole of NH3 because of 1-to-1 ratio, be left with half a mole. We're going to have 0 and 0 here to begin with, plus 1 mole, plus 1 mole. Right, so 1 mole of each of these products, which I just have right here. So we have 1 mole of ammonium ions, 1 mole of NH3. This gives us a buffer, right? Because we have NH3, which is our weak base, and the ammonium ion, which is its conjugate acid. Since they're both present, we have a buffer. So this is one of the ways you can go about making them, right? So please pay attention to this. You can make a buffer from a weak acid or base and its conjugate salt, or you can make it from a weak acid or base in excess reacting with a strong one. Now we'll actually look at the way that buffers resist changes in pH. Right, so we're going to look at the phosphate buffer. So this is the buffer that's in blood. This is the biological phosphate buffer. One of the two buffers you have in your blood, the other one's a carbonate buffer. Right, so this is dihydrogen phosphate and hydrogen phosphate. This keeps it around pH of about 7.4 roughly. If we add a strong acid to this, what's going to happen is the acid will react with our basic half of the buffer. It will accept the proton, forming chloride ion, and it will also form the acid part of the buffer. So what we did here is we replaced a strong acid with a weaker acid. Right? The weaker acid, we have to go in and do Ka calculations, but since it doesn't dissociate 100%, it's going to have much less of an effect on the pH than having just straight hydrochloric. Similarly, if we add a base, so let's say we add hydroxide, the hydroxide is going to react with our acidic part of the buffer, right? So the acid will donate to the base, so we're going to donate a proton here. We're going to wind up with H plus and HPO4 minus. So what we've done is we've taken a strong base and converted it into a weak base. Again, weak base has less of an effect on pH because it doesn't dissolve, it doesn't dissociate as much in water. So this is how a buffer is actually working. This is why it affects change in pH. Now this effect is not infinite. This effect only goes up to what we call the buffer capacity, which is the amount that you can add while still having both of the components in solution. Basically, this is just a stoichiometry problem, so all you say is your buffer capacity, for example, is 0.1 mole. That means that you can react 0.1 mole of acid or 0.1 mole of base, and you're going to retain the buffer. Once you get past that 0.1 mole, then you've already used up one of those two substances, and since you've used up one of them completely, it's no longer there, you no longer have the buffer. So let's get into the equation for calculating this. To calculate the buffer pH, you're going to use what's called the Henderson-Hasselbalch equation, or HH. And all this says is that the pH of the acid is equal to pKa of the, or pH of the buffer, is equal to pKa of the weak acid plus the log of the base concentration over the acid concentration. Right, so again, pKa just means negative log of Ka, and base over acid, right? So let's say that we were working with our phosphate buffer from the previous slide. We have H2PO4 minus and HPO4 2 minus. The base would be HPO4 2 minus because it has less protons over H2PO4 minus. So we just take the concentrations of those, the molarities, and that would give us the ratio there. Now, the thing to keep in mind is that if you are working with an equimolar buffer, so equimolar components of both acid and base, the log of 1 over 1 is 0, so the pH will equal the pKa. This number will come back to be very important later on. Right? So again, you just plug it in, you solve for pH, and it's pretty straightforward. Now, to make a buffer, so what you're going to do, and I would like to, once we get back, actually have you guys make and test these a little bit. All you do, so first thing you do is you take the target pH and you find some weak acid that has a pKa very close to that target number. Then you use Henderson-Hasselbalch to find the ratio between the acid and the base, so the molar ratio necessary. The buffer capacity tells you how many moles of the least populous substance you want, right? So for example, if we want something that has more base than acid, so if we want something that has a higher pH than the pKa, we'd have more base in there than we'd have acid. So the buffer capacity tells me how much of the acid to add, and the ratio from Henderson-Hasselbalch will then tell me how much of the base I use. And after that, I just make sure I figure out whatever salt I'm using. I always use sodium potassium ions because they're soluble no matter what. Alright, so that is basically working with a buffer and making a buffer. Again, hopefully we'll have some chance to do that in class. Now, one of the interesting calculations we can do is to calculate what happens to the pH of a buffer as we add acid or base to it. This isn't that as bad as it seems. All you do is just do some stoichiometry, right? So you figure out if I have my buffer and I add an acid to it, I react the acid with the basic component of the buffer, I change my concentrations accordingly based on how much I now have at the end. So you can do an ice table for this if you want. It's probably the easiest way to do it. And then after you get your value from the ice table, you just plug the numbers into your Henderson-Hasselbalch, and it gives you an answer. Now, one thing I should note is that the AP exam does not require you to do this math. Alright, so this will not be a question they will ever ask you as part of the AP exam. I'm asking you to do this, and we're going to do some calculation with this, because any first year college Gen Chem course is going to have you do this math. Right, so these are buffers. And buffers are going to be very important once we start talking about titrations.